First and foremost, I would like to thank the organizers for providing us this opportunity to meet and discuss mathematics, and of course for giving me the opportunity to give a talk. So the title of this talk is Weights and Approximation Problems. So the reason for this title was that initially I wasn't sure on which topic I was going to give a talk on. So I wanted to give myself some leverage. But then I decided that I will try to talk about Béchollet weights and Maukanapp weights, and these are somewhat connected to the Bergman projection and the Jaeger projection, respectively. And there's some joint work with Bartosz Malman and Artur Nicolau. All right, so let me begin. As an introduction, so the main point here is I will stay in the unit disk as Jose Pelayas mentioned. I will also do this here. So the main point here is I will try to keep the framework minimalistic in some sense, in order to keep it simple and in order to try to emphasis on conveying the main ideas behind this. So we will consider the classical Hardy spaces. I guess they don't need further introduction, and the Bergman spaces as well. And then an operator that will play a role here. Well, initially it will play a role. It is the so-called Cesaro-Voltaire operator. So basically, this operator is half a derivative. So basically, it's an analytic version of the classical paraproduct. So basically, I will talk a little bit about this operator in connection to some approximation problems and to weights. Okay, so let me first just recap on some earlier results on this. So one has this old paper by Pomerenke on univalent functions, where as a byproduct, he proved boundedness of this operator on H2. And then this was later extended by Siskakis and Oleman. And they proved that this generalized Cesaro operator is bounded if and only if the symbol belongs to the analytic BMO. And here I have assumed that this is a semi-norm, so I've assumed that G of 0 is 0. This doesn't change the operator because we're differentiating. And we have this form norm equivalence. And then later, this was done in the Hardy space setting as well. And here boundedness is equivalent to the classical block space. And we have this norm equivalence as well. So in some sense, these operators are understood via these symbol classes. And these are the symbol classes that I would like to emphasize on with regards to approximation problems later on. And then one could consider compactness as questions, and this has also been done. So basically, to recap the results, if you have little o conditions of the BMO and block respectively, this is the right condition for inducing a symbol, inducing a compact operator. And then there has been some study about the spectrum, at least for certain functions G. This has been done by Albert, Miller, Neumann, and then Young, and many others that unfortunately the margin is too short to include. But for certain rational functions and so on, this has been done, at least for logarithms and so on. So let us talk a little bit about the spectrum of these operators. So to this end, let us fix a P, and we will let X denote either the Hardy space or the Bergman space, so X will be either one of these spaces. And we suppose that this symbol induces a bounded linear operator. And then we would like to solve this resolvent equation. We would like to understand when is this operator invertible, classical question. And as I said, we may without laws of generality assume that G of 0 is 0. And lambda equal to 0 will always be in the spectrum. So we assume that lambda is non-zero here. And then it turns out that one can solve this equation explicitly. So this is sort of the point here. And well, if we would like to understand when this belongs to the space, then this is equivalent to e to the g belonging to the space, as by the formula above. So you can plug in a function which vanishes at 0, and then you can plug in a function which does not vanish at 0, and then you get these combined conditions. Okay, so basically, lambda does not belong to the spectrum, which makes this operator invertible if and only if this condition is hold. And for a long time, I mean, this works in general. I haven't really used anything about Hardy space, Bergman space. It's just point-wise things. So the point here is that for a long time, people had the conjecture that the number of that the spectrum of this operator should be the closure of the lambdas such that e to the g over lambda is in X. But as a harmonic analyst, you could think that, well, this seems like a weighted inequality, so maybe that's not really telling us the real story, the entire story. And indeed, it was not. So this was later characterized in more general setting than I am currently presenting here, but for the sake of keeping this simple, this was indeed a weight condition characterizing the spectrum. So basically, lambda does not belong to the spectrum if and only if the weight here is integrable, which was basically the first condition that I mentioned in the previous slide. And then we have this uniform reverse Jensen inequality. And then a similar thing was done later by our previous speaker, Jose Pelayas and Oleman, for Hardy spaces as well. Yeah, and these are, so let me mention a little bit about these conditions here. So for people working in weight theory, these uniform reverse Jensen kind of conditions on weight, these are better known as, at least in the Mockenhout weight setting, this is better known as the infinity condition. And there is one more important observation that we will use later. It is the following. Note that if plus minus lambda, because remember lambda was in the exponent, if plus minus lambda does not belong to the spectrum, then in fact this condition actually reduces to the A2 condition. It's some sort of a symmetry that we will come back to later on. And in a similar way for Bécquelet weights as well. But instead now the weights live on the disk and we take supreme over Carlson squares. Okay. Well, let us, so remember our weights were of this form with exponentials. Sorry? Okay.
I think it was just background noise. You can go on.
Right. So I would like to put to emphasis the following very cool observation, which actually I think let us fall in love with this problem to begin with. And it's the following observation. So with this connection with the spectrum of these TG operators and weights, the point is that one could deduce using operator theory, I mean, basic facts about operator theory, like the spectrum is compact, one could deduce deep Gehring type results on self-improvements of Mockenhout weights. So in fact, for instance, if V is an infinity weight, then greater power of W is an infinity weight. And this is quite cool that you have this connection between something very basic in operator theory, but to something very deep in harmonic analysis. And indeed, I mean, in the Mockenhout setting, this is quite general. I mean, these weights, as long as the weight is log integrable as well, then we can form the outer function. which has modulus equal to W, and and then we have that the weight is A infinity, if and only if the logarithm belongs to the analytic BMO. So this means that many weights are indeed of this form studied above, at least in the Makarov setting. So this was really a shock when I first read about this. Okay, so this was a very, very cool result by Pelias and Oleman. And then once we understood this, me and my colleague Bartosz, we thought, well, what if we go the other way around? What if we say that we would like to use weight theory in order to produce further insights on TGs and the symbol classes corresponding symbol classes? Okay, so these are the two main questions, and this is what I would like to address in this talk. It turns out that using similar things as compactness of the spectrum and using certain proofs of the weights, we can actually derive some geometric properties of the spectrum. At least we can derive things as spectral stability results of this kind. So suppose that we have two symbols G and H such that they induce bounded linear operators. And we suppose that one of the operator is quasi-nilpotent, so trivial spectrum. And then we have this following stability result. So by adding with H, we're not changing the spectrum. And in a similar way, we can derive the following properties of the spectrum. So if we have a TG operator and lambda is a non-zero element in the spectrum, then we can form a convex hull from, well, actually, let me just show you a picture. This is the easiest way. Basically, this is the result. So if you have a lambda in the spectrum, then basically the entire shaded region will belong to the spectrum. So this means that the spectrum will have this sort of star-shaped property. In fact, it will be simply connected, but it will also have some interior. And the idea behind this is basically, so if lambda is in the spectrum, then this means that e to the real part of G over lambda is not an infinity weight. And then, for instance, any point on the line joining 0 to lambda will not belong to the spectrum either, because that constitutes by multiplying the weight with some larger number than 1. So this is basically the idea. And then we can sort of tweak it a little bit to get some interior, at least for these points. And in some sense, I guess these results are sharp, because these shaded, diamond shaded areas they can be seen as intersections of circles. And indeed, the spectrum appears as circles in I think in almost every practical example that I've ever seen in this theory. Okay, so this is basically the ideas. Now we'll go into the approximation thing. So, of course, we consider the space-bounded analytic functions. And we have the following containments: H infinity included in BMO, analytic BMO included in Bloch. And remember, BMO was the symbol class for TG on the hardest spaces. And it shouldn't be little Bloch here. It should be just B. That's a typo. We have the following corollary of the first theorem that I stated above. So if G belongs to the closure of H infinity in analytic BMO or in the H infinity closure in Bloch, then the spectrum is trivial. And this is, just a brief sketch. It's a one-liner. It's very, very, very simple. So the point is that if you have a bounded function, then it's easily seen that even from the resultant formula that the spectrum is trivial. And then basically using this spectral stability theorem, which we're not changing this. So the modulus here denotes the spectral radius. So adding an H doesn't change the spectrum. And then we do the trivial bound. with a spectral radius, we bound it by the operator norm. And then we know that the operator norm is related to the norm of the symbol classes. And this holds for any h in bound analytic function, and then you just take the infimum and you get it. So very, very straightforward in some sense. But this structure stability is really a non-trivial thing. It's difficult. It's not easy to see from the formula a priori. And then you could ask, what about the converse? It's a natural question. So what if we say that the spectrum is trivial? Can we say something about approximations? Well, it turns out that we can do this, and this is the content, the result with Bartosz. So we managed to characterize the H-infinity closure in analytic BMO with this condition. And yeah, so basically the sketch is also is not as difficult once you state the ingredients. So we use the deep theorem, and we note that the spectrum is trivial if and only if, remember, so if the spectrum is trivial, then this means that plus minus lambda belongs to the spectrum for any lambda. And then we actually get that the real and imaginary parts are A2 weights. But then there is this deep theorem by Helson-Jego, which relates the distance to L infinity in the BMO norm to this quantity here, which is the infimum of the constant such that e to the phi. And well, but we're interested in the distance to H infinity because we're taking H infinity closure in BMO. Well, there is a deep result by Sarason, which says that for analytic BMO functions, the distance to H infinity is comparable to the distance to L infinity. And this is some sort of a duality trick that is being done. And then basically combining these, we get the theorem. Okay, and so this was the Hardy space setting. And then you could ask, well, what about the Bergman? Well, what about the Bloch? So say that e to the real part of g over lambda is in B2 for any lambda, non-zero. Does this mean that we can characterize the closure of the Bloch? Indeed, this was an open problem by a Reine paper by Anderson, Clooney, and Pomerenke a while ago. And this has been open since then. So, I mean, it's natural to ask this conjecture that we had in the previous slide. Let me see here. That's the converse of this theorem actually should hold. Yeah. And the point was that actually I went to, in 2019, it was yet another INDAM conference where I met Artur, and it was a very nice conference. I remember I was walking and I was telling him about this, and we got both very excited and started working on this. Well, and it turns out that the result is false, and this is a bit somewhat striking, but not striking at the same time. And let me explain in the following sense. So we can find a Bloch function such that this weight, or equivalently the spectrum, is trivial, but the Bloch function does not belong to the HP closure in Bloch for any P. So this is quite different. So in some sense, this is sort of the first time where this theory for analytic power products parts away in the Hardy space and the Bergman space. So things are quite different. But at the same time, I mean, Bécquelet weights and Markov weights are quite different as well. So in some sense, maybe it's not that unexpected. But nevertheless, we started working on this. And the main idea was using tools from earlier work by Makarov. And basically the ideas were, instead of looking at analytic Bloch functions, we tried to discretize the problem and try to investigate dyadic martingales with uniformly bounded jumps. And then basically try to construct a counterexample using the martingales, and then go back and see that this counterexample constitutes to a superlacunary series. So this, yeah, it was, so this, yes, I will not go into the details of this. This was probably the most technical part in that paper. So So what is so the remaining question here is now, well, okay, so this condition here with zero spectrum, or this B2 condition, it doesn't capture this H-infinity closure. But what the heck does it do? So what is it? How can we understand it? Does it give is it meaningful to study it somehow? And well, it is a natural question. And indeed, we shall answer this question soon. So before doing that, we define the following space BMO on the disk. And this consists of complex valued functions, normed, well, this is a semi-norm, of course. And now I'm taking the supremum over disks centered at point in the unit disk. And I can let the radius vary and so on. And the point of considering these spaces is that by earlier works, or by Koifman, Rotberg, and Weiss, they showed that these spaces, I mean, the block space is essentially the analytic functions in this space. And then from this, well, okay, so first we recall the spectral radius. So we denote the spectral radius by this of TG on LPA. And then by the Allemann-Constantin theorem, this will basically agree with this infimum. So basically, the infimum of lambda such that the entire circle, going around the entire circle in zeta, this will be a B2. Using this characterization, we can give a description of the spectral radius, and this basically characterizes. And this is the content of our next result. So basically, it turns out that this spectral radius is actually related to the L infinity, but now on the disk, the distance to L infinity of a Bloch function. And I mean, in this sense, I mean, these spaces are horrendous somehow. I mean, these are large and non-analytic, and they are not as, so this doesn't really tell us much. But this is the result, and you could ask, well, can we understand them in a better way? Well, we can actually. So let me give you a more practical way to understand them. So recall the hyperbolic metric on D. Then recall the well-known fact that the hyperbolic Lipschitz class defined via the semi-norm, the holomorphic functions in this class are actually isometrically isomorphic to the Bloch. And this is just a calculation, actually. So the Bloch function can be understood as hyperbolic Lipschitz functions that are holomorphic on the disk. And then we can actually understand the spectral radius with respect to the following condition here. So given a Bloch function G, we let the epsilon of G be the infimum such that, so that we have this quantity here. So basically this is somehow related to the Lipschitz characteristic of the Bloch function. And now, I mean, this is just pointwise now. We don't have to deal with some strange L infinity on the disk, which we don't really understand. And then we have, I mean, this pointwise analytic functions now. And then we can relate the spectral radius in this way. Yeah, so that's a different way to put it. And yeah, so with that, I guess we managed to answer some questions. Unfortunately, the open problem of characterizing H infinity Bloch remains open, and it shows that this naive approach unfortunately doesn't capture what's going on here. And yeah, I guess okay, yeah. So maybe if I have time, I have until 1/4 right?
Yep.
Okay, great. So maybe I'll sketch a proof of this L infinity. So let me see. This is the theorem that I would like to sketch a proof for.
Maybe leave just a minute if there are questions. Just
yeah.
Is that what everybody else did? Okay.
seems not to be any questions. Can I continue?
Mm-hmm.
All right, so let me see. So this is the theorem that we would like to prove, at least just sketch. So the following observation, so we would like to reduce this quantity because we had this rotation. So basically we reduce this inequality. It's basically a standard reduction. Changing unimodular constant of G doesn't really change the spectrum, just rotates. So basically we can prove something about real valued functions. So this is the quantity that we would like to prove. So there is a reduction step, and I will try to justify the sketch of this proof. Okay. And now the lower bound is basically just the John-Nirenberg inequality. So the John-Nirenberg inequality says the following, that at least phrased as being a B2 weight. It says that there exists a universal constant such that e to the c phi divided by norm of phi, BMO norm of phi, is a B2 weight. And then, of course, we're not changing the B2 constant by adding a bounded function. So yeah, so this is the lower bound. So for the upper bound, we will do some, so let us be given a weight, and we denote by WQ the average. So Q here will be an Carlson square. And then by standard Chebyshev inequality, this is what we get. However, if our weight is a B2 weight, then there exists a constant CW, which is uniform in Q. And then using Chebyshev, we can derive this as well. And then combining these two, so combining this with this, we actually arrive at the following. And if we pick lambda equal to the logarithm of t times this B2 constant of W, we get the following. So this is some sort of a uniform John-Nirenberg type inequality for logarithms of B2 weights. Okay, and then we would like to apply this to the weight e to the phi divided by alpha, such that, well, e to the phi divided by alpha is a B2 weight. I mean, for these B2 weights, we would like to apply it, and what we get is this. And here, of course, is at an additional cost of maybe changing the constant c of phi, but that is not really important here. And then we make the following observation. So if we take a disk centered at the unit disk with the radius less than the distance to the disk divided by 2, we recall that since phi is the real part of a block function, block functions are uniformly bounded on hyperbolic disks of fixed radii. So alternatively on top Carlson squares, they're uniformly bounded by some constant times the Bloch norm. It's basically, you can see it from the Bloch condition. And then when the disk is greater than the half of the distance, then we basically pick a cube that covers that disk with the following property, and then we apply 1, and basically combining, we get the following. Of course, we get a lot of other constants there as well, but this is what we end up with. And now to the final stage. Using this, we make the following observation, that a function in BMO can be extended to a function in BMO of R2 by simple reflection. And then from that, one could derive this distribution of inequality. Again, C phi is another constant that is possibly changing. And then the point of doing this is to use this Garnett-Jones type distance formula, which says that it works for any D. It was in RD, but we will use it for R2 here. And And then from that, we get the result. So this is basically the sketch that one puts oneself in the framework so that we can apply this deep theorem by this Annals paper by Garnett and Jones. Yeah, and that's I guess that's basically it. I would like to thank you for listening, and